this works. Hello, hello. Here we are again. Took a break, had some food, watched a couple of videos, took some time. Let's see how we doing. Had some food, watched a couple of videos, took some time. Let's see how we doing. Had some food. It looks okay. So sweet. Yeah, welcome. And let's continue. Let's keep going. Fibonacci sequence. All right, let's go. So these problems are getting progressively more challenging. It seems. Or a generator function that returns a generator object, which yields the Fibonacci sequence. Okay, first few numbers are okay. You ready for this one? This is a fun one. Okay. Let n be 1, and then what is this? What is the syntax? Hold on. Oops. What is this syntax? Some JavaScript syntax? Generator object. What is a generator object? Iterator that can be paused and resumed. Huh. It should be implemented. No, don't. Wait. Oh. Function asterisk. Or, yeah, it's asterisk. Yield value. Okay. Yield pauses execution, returns value. Oh. Huh. Huh. Interesting. Okay. Let's do let a 0 equals 1. Current equals a. Maybe we'll do the following. Let call count 0, call count equals 0, yield 1. I'm not really sure about this. I don't know. Could try this. Something like this. Buffering. Watched a couple videos. Buffering. Watched a couple videos. Still buffering. Not sure what to do about that. Give me a moment here. Okay, I don't think we're buffering as much now. Okay. There we go. Interesting. Okay. Let's do a third case. Huh. 001. Okay. So that's not correct. Interesting. Um, hmm. Um, huh. I don't write generators very often, as you can probably tell. Does this work? I don't know. Does this make sense? Huh. Um, could do this. No, can't do that. Hmm. Um, yeah, I mean, uh, could do this. Suppose. I don't think this is correct though, right? No. There we go. That works. All right, let's go for it. See how this goes. Temporary variable works nicely. It's pretty good. Oh, I forgot something important. Uh-oh. Oh, I did forget something. Oh, hold on a minute. Oh no. I'm gonna have to start over. Oh no. Coding car, what's up, Harsh? Welcome. Hello, hello. Howdy. There we go. Okay, now it's working. I forgot to get the chat. Give me one moment. In the car, yeah. Not driving, but in the car. What's up? So, let me get the next question up here. Just give me one moment. Doing some tinkering here. All right. I like being in my car. It's familiar. It's comfortable. All paths from source to target. Okay, so this one I already solved, but I'll describe the answer or a solution, potential solution. Let's look at how long ago I solved this though. Python 2019. Let's do it in C++. We'll do it in C++. Given a directed acyclic graph of n nodes labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1, return them in any order. So, interestingly, DAG-related questions lend themselves to either memoization or dynamic programming. All right. Find all possible paths. Okay, list of all nodes you can visit from node. There's directed edge from node I to node graph ij. All right. So 2 paths from 0 to 3, 0 to 1 to 3, 0 to 2 to 3. So, like what you would do for this question, for example, let's say this 3, let's say you wanted to get to 4, or and there was a path to 4 from 3. Instead of following every path 0, 1, 3 to 4 and 0, 2 to 4, you would figure out all the paths to 3 and then combine that with all the paths from 3 to 4, for example. That's kind of how DAGs and dynamic programming kind of optimize code. Okay, so let's see, you've got, how big is the graph? 15 elements, no self loops, elements are unique, it's guaranteed to be a DAG. It's a relatively small graph. So example 2, we want to go from 0 to n minus 1. So looks like 0 to 4. So there's one path. There's a path to 3 to 4, path to 1 to 2 to 3 to 4, 1 to 2. So for example, the paths from 3 to 4, there's only one. And so you take all of these other paths to 3 and append them to the path from 3 to 4 in order to optimize the code. There's also one from 1 to 4. Let's see if we get all those. 0 to 4, 0 to 3 to 4, 0 to 1 to 2 to 3 to 4. 0 to 1 to 2. Oh, I did that one already. 0 to 1 to 3 to 4, and there's 0 to 1. Yeah, that's interesting. Okay, so I'm going to do this in C++. Well, I could do something like the following. So I'm going to try memoization. I think it's a simple way to go. Or actually, we could do it this way. We'll say paths. And we'll do this kind of thing. So graph size. And these will be, I guess, empty vectors. And we'll use the backtracking approach with a memoized backtracking approach. So it takes paths and graph. And what we're going to do, we're going to use an int for the node. And I'm going to call the backtracking routine. We're going to use recursive, use RR for recursive routine, I guess. And then we're going to basically just return paths of 0. So what we're going to say is if paths of node is not empty, then we return paths of node. Explain that shortly. If node is equal to n-1, which is just graph.size -1, then we're going to return std vector int with just graph size to -1. Okay. Then we're going to say std vector int result and return result. Going to say for const int children in graph of node. Something a little bit awkward here is I think we're going to build the paths backwards in reverse. Build them in reverse. So we're going to say for each child, we're going to say result for recurse. Const auto reference for each vector and the recursion of the child. We're going to append, we're going to say, we're going to create a copy, v.pushback this current node, and then result.pushback v. And then we're going to set paths of node equal to this result. Yeah. And we're going to std move. Okay, hopefully this makes sense. Yeah. Something like this. What's up, chat? Are you preparing for a job? How old are you and from which country? I'm from the USA and I'm over 30. Over 30. I'm not really preparing for a job. Not exactly. Not exactly. Okay, it's ambiguous. Actually, I should have done. I think this should clarify the ambiguity. Cannot be narrowed. Okay. I might just need to static. What's that called? Cast. Maybe that'll work. Let's. Int const. Oh, this is not supposed to be. Oh, oh, it's not const. Oops. Whoops. Oh, you know what? This is incorrect. This is actually, it should be a vector of vectors, I think. It's a little bit confusing. Yeah, okay. Let's do it this way. That was a mistake on my part. Maybe, yeah. Okay. And yeah, it's supposed to be a vector of vectors. Right. That's a mistake on my part. Yeah, it's actually three-dimensional. Whoops. Three-dimensional. Oh. Whoops. Oh, that's a rough one. Oh boy. Yeah, I think that's correct. It's three-dimensional. Yeah, it is. Oh boy. You boy. This may not be much better. Okay. Output. I also have to reverse all of these at the end as well. Okay. All right. So when I backtrack on 0, I'm going to look at the children of graph node, which, yeah, be 0. Let me see here, this test case. 0, so it should be 1, 2. Excuse me, then for each child, we're going to recurse. And this is going to return these paths with the, let's see, the base case, eventually the graph size minus 1, which is, okay, 1, 2, 3, 4, should be 3. So eventually I get to 3. And I'd have a single vector in there with a 3. And paths.node is not empty. Let me return that. Sure. What's wrong here, though? That's the question. I think it looks okay. Something's wrong, though. Something is wrong because I'm not getting anything in the output. Which probably means I'm not reaching this base case. So let's just make sure that's happening. That should definitely be happening. If it's not, there's something strange, something I missed is going on here. Yeah, it's not being reached. Okay, that should be reached though. I don't know why that's not being reached. Yeah, 1, 2. So I should reach 1, 2 and recurse on 1, 2, which would be let's recurse on 1 to start. So I'll recurse on 1. I would then would not go there, would not go. Oh, actually, no, it should be empty. Oh, maybe it's not empty. Oh, maybe that's the issue. I don't know if this counts as empty. It's not empty. I see. Maybe I can do this. Maybe that's the issue. Okay, now it's being reached. But I don't have the wrong output. Okay. Hmm. Right, but why am I getting an empty? Why am I getting empty output? Something subtle going on here that I don't realize. About this one. Okay, I got some kind of output. Not obvious as to what's going on here though. Let's see. Let's just see what the path is where it stops. This, I think, will print kind of in the reverse. I think sort of reverse. Zero, 1, 3, 2, 3. Okay, so it's following 0, 1, 3 and 2, 3. It's following the right paths. Why isn't it doing what I want it to do? Should return 3 here. That should be fine. Okay. Let's do more debugging. Yeah, I'm not quite sure what's wrong. Something odd is happening here. So 013 subpath size 1. Subpath size 0. Oh, there we go. Now it's printing. What the heck? Wait, what? Wasn't doing that before. What happened? Oh, it may have been optimized out, the code. Maybe it's a compiler optimization. Oh man, I think the compiler optimized it out. That's super awkward, huh? That might be it. It could be a compiler optimization that I'm not aware of. That's very awkward. Or something going on here that's not obvious. I don't know. I don't know. No. No, it's not a compiler optimization. It's something else going on here. Oh, that's why, because I moved it. That's why. Oh, that's my mistake. I didn't realize. That's my mistake. Of course. Oh, duh. Duh. I was trying to optimize by using a move. Oh my gosh, that's really silly. That's goofy. That's my mistake. I don't know what. Oh, that's bad. Is this child or these children? That's a big mistake on my part. Trying to optimize by using the oh, that's very silly. That's pretty goofy. Trying to optimize by using move semantics, but actually just breaking your code. I was like, what did I do? I must have done something subtle. Yeah, that was a move semantics issue. This is going to be auto result instead move. It doesn't really, you don't need to move it. Doesn't matter much. And then for, oh no, result equals paths of 0. Actually, you could just do this. Or auto reference B in paths of 0. Instead reverse, that begin, that end. Just reverse all of these paths afterwards. I think that's what's required at the end. Yeah, there we go. Okay, very nice. I think I'm going to try it, see where it goes. Let me see how we're doing stream health, stream-wise, if we're still live here. Oh, it's took doing stream health, stream-wise. Oh man, it's already been 30 minutes I've been on this. Oh boy. Okay, the stream is healthy. Dang, not a very efficient solution, huh? Not the most efficient solution. A lot of extra copying goes on here. Yeah, this is actually not the best. It's memoized, but there's no real reason to memoize this, I think. There's a better way to do this, and that would be just use a single path. And use... There's a better way to do this. Path. In this case, it's a little more efficient to do it this way. Okay, now let's do it this way. Instead of paths, we're going to just do a single path. We're going to say when we get to this end here, we're going to return, and we're going to say result.pushback node. Oh no, pushback path. And what we're going to do is for each child, we're going to do the following. We're going to say path.pushback child recurse, and then path.popback child. We'll do it this way. And then keep it simple. So this won't do any memoization, but this is a much simpler approach. And it'll be faster in this case. And I think we just do for each result, we just reverse. Yeah, this is much simpler, much faster to program. And it'll be a faster runtime too, because I won't have all the extra memory. 3.1, 3.2. Got to push the 0 on there. Okay. Oh, I guess I don't have to reverse it. Forgive me. Okay, let's try that. Yeah, it's a much easier to program, easier to understand approach. There we go, 0 milliseconds. Great. How are we doing here? The stream health is good. About 40 minutes in, that's okay, I think. Yeah, 100%, that's pretty good. Okay, next. I'm trying to go to about 3 hours here. Let me solve a couple more. Maximum product of 2 elements in an array. Given the array of integers nums, you'll choose 2 different indices I and j of the array. Return the maximum value of nums of I minus 1 times nums of j minus 1. Okay. Okay, interesting. Excuse me, if I just want to maximize nums of I and nums of j. I think this is always just the 2 largest numbers multiplied together. I could be wrong, but I think that's the case. Yeah, it's just always the 2 biggest numbers. So, largest and I think these are always positive numbers. Let's see. Yeah. Penultimate. And we're just going to go ahead and return largest minus 1 times penultimate minus 1. I think you could prove this is always the case. So if, actually, you could even just do x. You don't need all this. So if x is larger than penultimate, then penultimate is x. If penultimate is larger than largest, let's swap penultimate, largest. I think this is sufficient to get the top two largest values. You check it against the smaller of the two. Yeah, there we go. I think this is always right. Let me try this. You check it against the smaller of the two, and if it's larger, then you upgrade the smaller, and then you swap the two if it's also larger than the largest. So it's a pretty straightforward solution. I'm just gonna submit it again. Yeah, it's pretty good. I like that. Okay, not bad. Unique Morse code words. Let's see how long ago we submitted this. Python. Yeah, we'll do it again. International Morse code defines a standard encoding where each letter is mapped to a series of dots and dashes as follows. A maps to dot dash, B maps to dash dot dot, C maps to dash dot, and so on. For convenience, the full table for the 26 letters of the English alphabet is given below. Wow, okay, that's Morse code. Given an array of strings words where each word can be written as concatenation of the Morse code of each letter. For example, cab can be written as such, which is the concatenation of these different letters. We will call such a concatenation the transformational word. Return the number of different transformations among all words we have. Transformation of each word is Jinzen gig message. There are two different transformations. Oh, okay. Let's see. So if I get the same transformation, then I don't count it. Okay. Interesting. All right. It's only 100 words, so I guess I could just use a vector of strings and then deduplicate it. Let's look for a good way to deduplicate. I think I would normally like sort it and then sort unique, I guess. Yeah, sort unique is probably the way. Sort unique, erase. An unordered set works, but it's not as efficient and when you're using a small number of things. Okay. So let's look at this mapping here. So we'll do const std vector std string mapping. I think this works. Okay. Then we're gonna say std vector std string transformed. I'm going to say for const auto word w words const char ch and w string current. I'm going to say current plus equals transformed ch minus a, and then we're going to say mapping transformed back, and then we're going to say student sort transformed. I'm just going to call this t. It's taking student characters. T dot begin, t dot end, and then stood erase stood unique. What did they use? Oh, that's it. It's just unique, and then unique is just going to be beginning ending. Okay, it's pretty easy. And then return t, something like, or return t dot size. This is probably one of the easier ways of handling this. Doing this in Python is oh. Does this approach work for strings? I guess it doesn't, because the compiler is complaining. Compiler is like, no. Oh, vector race. Oh, that's why. There we go. Oops. Fine. All right, I'm going to go for it. Okay, not the most efficient, but it should be fast enough, I think. 3 milliseconds is okay. Yeah, there we go. All right. What's next? So, also, how are we doing on time? 48 minutes. I might stop after an hour. We'll see. Keep going here, but yeah, I want to do that in C++ because I solved it last time in Python. Yeah, this next one is replace employee with the unique identifier. It's also MySQL. Let's see. The unique identifier. Okay, employee ID. ID is the primary key for this table. Each row of this table contains the ID and the name of an employee in a company. Well, let me see. Okay, I can speak a little more loudly now. ID is the primary key with this table. For this table, each row of this table contains the ID and the name of an employee in a company. Okay, so we have employees, you have employee uni. ID, unique ID is the primary key for this table. ID name, unique ID. Okay, each row of this table contains the ID and the corresponding unique ID of an employee in the company. Write a solution to show the unique ID of each user. If a user does not have a unique ID, replace just show null. Turn the result table in any order. Result format. So this is a join. Here's the result. Output unique ID name. Okay. Yeah, this is a join. So hold on, select from I think it's a right join, by the way. Employees, right join. Excuse me. Oh, forgive me. Probably should get a mute button. An employee uni. Employees, right join, employee uni. Jeez. Jeez. Okay. Let's see. I think it's just join right, maybe. I think it's right join. I might have to use opening and closing. On ID. I think it's a right join on. Something like this. Oh. And I need a right join. I think it's a right join. There we go. So now, no. It's a left join, actually. Let me see. Let me see. There we go. Now we have the null values. Now we just want the unique ID, name. Yeah, the left join. Okay. Something like this. There we go. Let's give that a shot. All right, think about an hour. Take a break. Quick break, short break. That's pretty good. Yeah, that's fine. I'm not gonna go too crazy with the SQL stuff. Okay, this one was C++. All right. This one I solved a little bit earlier, 2023, a few years ago. I'll just describe how this can be done. You have n tiles where each tile has one letter, tiles of I printed on it. Return the number of possible non-empty sequences of letters you can make using the letters printed on these tiles. Okay. So these have A, B. Possible sequences are A, B, A, B, B, A, B, A, B. Oh boy. Possible non-empty sequences of letters you can make using the letters printed on those tiles. Okay. So basically you have, I think it's, this is a monomial question. I think, no, this is actually kind of a complicated combinatorial question. Let me say I don't know the answer immediately. I want to say numbers between 1 and 7, so it's not too bad, but basically, if you didn't have any duplicates, it would just be the permutations, right? Which would be just the number of tiles factorial. However, it's a little more complex than that because some of these permutations will be equal to each other. So it's going to be the tiles factorial divided by the frequency, each frequency factorial. So I'll show you what that looks like. I'm pretty sure that's what I submitted. I'm sure that's what I did. But that's the answer. Yeah. So you get this. Oh yeah, and then I calculated oh wow. It's way more complicated than it needs to be. I made that a lot more. Let's do how correct one. So we're gonna do static int frequency 26 std fill frequency equals 26 0, and we're gonna say for each tile const char ch tiles plus frequency of ch minus a. I'm assuming these are all uppercase letters. Just double check. The uppercase, okay. Then we're going to do, quickly we can do just factorial from 1 to 7. So fact 0, static, factorial. This is going to be, there's only 7 of them, right? So it's going to be 0 is 1, 1 is 1, 2 is 2, 3 is 6, 4 is 24, 5 is 120, 6 is 720, and 7 is 49,000 plus 140, which is 5,040. Right, that's 0, 1, 2, 3, 4, 5, 6, 7. And then we're just going to say for, say its result equals fact of tiles.size, return result. We're going to say const, or no, int times 0, I is less than 6 plus plus I, result, divide equals fact of frequency. Really straightforward. It's a multinomial expression, and it's wrong. Output 3, expected 8. Oh, wait a minute. Oh no. That doesn't include all of the smaller cases where you have one less tile. Oh, I forgot. There's a lot of different ways to calculate this. Oh no. Oh. Oh no. So this is maybe not the right way to solve this. That's a bummer. Okay. Maybe dynamic programming could be useful here. I'm not sure. It's super awkward. The problem with what I'm about to do is that I can run this subroutine on every subset of tile selections, but that's very awkward. Shoot. Yeah, it's a little bit awkward. You think if there's a better way to do this? Okay. Excuse me. Like I could say 3 choose 2 here, but the problem with that is that it's if I choose the 2 A's, then I would need to divide for each of those. Oh, that's awkward. Gulp, gulp. No. All right, this is not really correct. Never mind. No, I have to come up with a better idea. Okay. Let me see. So that was wrong. That's just the wrong answer. Darn. You know, sometimes you have a simple answer that's wrong. Simple, concise, efficient, and wrong. All right. Let's try dynamic programming. We could select this element or not, right? And if we do select that element, how many other elements can we choose from? This is an awkward one. I mean, I can use could use memoization here too. It's just awkward. Yeah, I mean, that's probably the easiest way to go. Gulp. That's probably the easiest way to go. How about we do this? Um, 2 to the 7th is not that large. 2 to the 6th, I think, is 2 to the 6th is 64. 2 to the 7th is 128. Right. Oh, but if you go 2 to the 8th, it's 256. Yeah, so it's going to be for each. It's fine. I think it's fine. It's 2 to the 8th. I'm thinking about this. I'm wrong here. 2 to the 7th. It's more like 2 to the 8th minus 1, I think. More like 2 to the 8th is the upper bound. In any case, we're going to just sort in unique possibilities at the end. We'll just dump everything in there, everything that's possible. Keep it simple. And then we're going to say, I mean, a really simple way of doing it is using bit manipulation. Starting with 1. I kind of dislike that though. It's like not my favorite thing to do. The other approach would be like a backtracking. Yeah, this might be better. We could do it this way. It's fine. So we're gonna say stood string current for ints j equals 1, j bit shift 1, j is less than that size, or really just say count. Hopefully this makes sense. Could do a bitwise operation here. H bit. There's 3 tiles. You bit shift 1, 1, 2, 3 times. Yeah. Okay. And then J gets shifted from 1 once, twice, 3 times. So count would be 0, 1, 2, 3. After 3, it stops. Yeah. Okay. And then we would say if I and j, then current plus equals tiles of count. Excuse me. Oof. Oof, man. Then after that, we say possible to push back. Correct. It's something like this. I mean, this is a little bit more involved, I think, than whatever I did previously. I think the thing I did previously was more of a math-based approach. This is more of a direct kind of calculation. So maybe it's good that I did this again. Excuse me. Wrong. Okay. 5 should be 8. So this one ends up being fine, but this one is not. Excuse me. Debug. Const auto reference. String and possible. What happened? What happened? All right, I think I'll probably take a break here after I'm done, and then stream again for another couple hours. I think take a break for a few minutes. What does my debug look like here? Okay, A, B, A, B, A, B, A, B. Oh, the problem here is the permutations. Right, that's my mistake. No, I mean, yeah, I see. That does make sense, actually. You'd have to run this routine on every, like, permutation. It doesn't work either, does it? No, it doesn't. That's pretty awkward. Yeah, it's an awkward one. Okay. I'm trying to avoid using a backtracking algorithm, but it's kind of hard not to use a backtracking algorithm. Excuse me. Trying to think of a better way to do this. I mean, backtracking is fine. It's fine. It works. It's okay. We can go with backtracking algorithm. I think there's a better way to do it, but we're not gonna go into all those details here. We're just gonna try to backtrack. Okay. Possible. Possible. This. Yeah. Let's observe. We're gonna go with 5040. Let's actually make this static. Yes. Okay. Now we're gonna use backtracking. And we're going to say constant index. Backtrack. And we're going to std sort. Std erase. Possible erase. Std unique. Possible begin. Possible end. Possible. Okay. and then return possible size. Okay, this is more of what I want to do, I think. Backtrack on the 0, I think. So we can say and I think a bit mask is also appropriate here. So the way we're going to do this is the bit mask is going to be 0 initially. So nothing and nothing. What we're going to do is say if bit mask is all ones, which is going to be tiles, one tiles dot size minus 1. So we've used all the bits, then we're done. Otherwise, we're going to say if one bit shifted index and bit mask really, I think it's just going to be going to have a current string. Come back to this in a moment. I'm not really sure how I want to do this. You give different possibilities here. Yeah, I mean, okay, I guess. So if bit mask and ix this is confusing. Still not sure how I want to do this. Could use a -1 here. I could use a 0 here. I gotta think about this a little bit more. So if why don't I just push this back every time? Well, I want to use that bit mask. I suppose I'll use it here. I don't know. I don't know. I don't really know. Why not? Why not just put it here? And just put the pushback here. Whatever. Okay. Mm-hmm. Okay. So if this bit hasn't been set in the bit mask yet, then we're going to add this character tiles of height. And then we're going to push back this current value. And then we're going to update the bit mask and increment the index. Actually, there's no index. It's just a bit mask. There is no index. There's just a bit mask. That might be part of why I'm a little bit confused here. Yeah. Well, golly. Well, golly. Okay. What does this do? Compiler. Oh, okay. Forgot that's static. Okay. It's lower precedence, or it's a fair point. That is a fair point. Oops. Also important. Also important. Wrong answer, though. Oh, no. 1. Output of 1. Okay. Not quite what I was expecting. Okay. Oh, it's not. That has something to do with it. There we go. I'm just going to go ahead and go for it. Just going to go ahead and go for it. See how this goes. It's accepted. It's slow, but it's accepted. This is not a great solution. Definitely not. Okay. Also, for some reason, can you please? Also, for some reason, my accepted solution is no longer in the in this section over here. Or okay, there we go. Okay. Maybe I'll look at my previous solution then. Okay. This is not the best solution. This is not a great solution. It's a backtracking solution that's kind of unnecessarily slow. Is it quick to program? Not really. What is going on with this? Huh. Okay. So the current backtracking recursion with bit manipulation suggested backtracking recursion counting, generating unique permutations from multi-set using backtracking with frequency counting. Huh. Current complexity O(n) factorial times n suggested complexity of 2 to the n. Switch to counting frequencies and backtracking directly to avoid generating duplicate strings entirely. Okay. So the approach, suggestion for efficiency, code style good, structure excellent, avoid static vectors for state, declare them locally to ensure thread safety and clarity. Interesting. I wasn't expecting that. Let's look at my previous solution. Huh. Oh, not that one. Oh, no, not that one. No, no. Shoot. This is what I wanted. My previous approach was clever. I don't remember what I did, though. It's a while back. Let's try it again. Yeah, I went back with backtracking because I simply forgot what I did last time. Came out okay, but it wasn't the best. All right, what does this do? So have the factorial function, which I did something wrong here, didn't I? I think I did. What did I do, man? I copied incorrectly. Hmm. Oh. Hmm. So this one's correct. 2. What does this do, though? It's been a while. This is like a very fast solution. But what did I do? Okay. So these factorials, I could have just calculated that directly and put it into a static array. Unordered set of strings processed, result frequency of 26. Int I, current string, fill frequency. Current plus equals tiles, increment frequency count of A. So, okay, it's very similar to what I did before, actually, but without backtracking. All right. Then I sort current begin, current end. Okay, if I haven't already processed this permutation, then insert it to branch processed. Then calculate the factorial of the size. Oh, okay. So I did actually just do every permutation. Every permutation, every size. I was like, oh, that's going to take too long to calculate, but actually it's efficient to calculate it. It's just this factorial, multinomial factor that I described before. But I would just write the frequency. Oh, I see. Okay. All right. And the ones that were duplicates, I just tossed them out using. Well, that was clever. That was a good idea. I didn't even think to do that. This could be optimized a little bit. Yeah. So I still use the multinomial factors, but what I optimized for here is I went ahead and used an unordered set of strings that I've already processed. So I used a little bit of memoization. So I would sort what I've got, and then not I would sort what I've got and then use that as a way to ensure that I don't use that as a key. Is this slow? I don't think it's slower. Sort what I've got and put it into a basically a hash set, and don't repeat processing routines parts I've already seen, and then calculate the permutations directly using a multinomial expression. Very clever. Very clever. And like I mentioned, the multinomial expression is as simple as calculating the frequency. I wanted to avoid, excuse me, maybe it's bad on my part to avoid things like memoizing with hash sets. I wanted to avoid memoizing with a hash set. I just wanted to avoid that. It felt bad to use that. It felt bad to use the hash set on all of the different permutations. One can actually optimize this hash set by utilizing the frequency map here. And you can actually convert the frequency map into basically a base 26, a 7-letter base 26 number. But 26 to the 7th is kind of a large number. I think it's let me see if I could calculate that right now. 26 raised to the, I think it's raised to the 6th, not the 7th. That's a really big number. It's not going to fit in a 32-bit integer. Yeah, it's 9 digits. So it would be, you could use a long for that though. Instead of, but that would still be a hash set. So a hash set of strings is probably fine. Yeah, I think that's probably the best way to do it, the only realistic way to do it. That's a cool solution. I like this solution. What is the, oh, okay. I gotta subscribe for more analysis. All right. I was gonna say the analysis is cool. I like that. All right. So, I mean, yeah, my previous solution was definitely, I shouldn't like not allow myself to utilize things like hash sets. I should probably use hash sets a little bit more. I don't like to use hash sets because they're a little bit slower than other options typically, and so I tend to avoid them. But in situations like this, if you like tie your hands behind your back and don't use a hash set, then it's just not as good of a solution, I think. Like the solution that I gave didn't use a hash set, but actually I think I'd still use the hash set anyway. I didn't really use the hash set. I used I did a sort unique at the end anyway. And yeah, it passed the test cases and it was efficient enough, but it was overall a lot slower than it needed to be. Whereas using the hash set combined with the multinomial calculation and a direct factorial calculation made things a lot more efficient. And so it's an interesting question. It's a good one. Popular one too. So yeah, thank you for watching. I think I'm gonna take a break here. About an hour, almost hour and 40 minutes. I'm gonna stop here. I'm gonna take a break for a bit, and then I'm gonna, I think, start the stream again for another hour and a half. We'll do it that way. Yeah, thank you again for watching. And if you like the stream, don't forget to like and subscribe, all that good stuff. Comment too if you want. Yeah, let's go with that.